Syrtis Major stretches across ancient Martian plains. Dark eroded rock cuts through lighter dust. Sand dunes migrate steadily across the surface. Beneath them, older rocky material is exposed. Wind redistributes dark grains across the ground. That motion strips fine surface dust away. Subtle reds, blues, and browns emerge in patches. Hummocky mounds rise along the margin of Jezero crater. These plains rank among the oldest terrains on Mars. They preserve erosion, sediment transport, and deep planetary time. HiRISE team noted, wind-driven sand reveals underlying geology. Gordiae Fossae lies within a volcanic region near Olympus Mons. Smooth lava plains dominate the landscape. Long, narrow fissures slice across the surface. These troughs form as underground faults propagate upward. Magma movement likely weakens the crust from below. Surface material collapses inward, forming pits and elongated trenches. In this case, erupted material escapes the fissure. It flows outward across the plain and cools. The surface preserves this motion in stone. The structure exposes active volcanic plumbing beneath Mars. Coprates chasma cuts deeply into Valles Marineris. The canyon floor lies more than 7 kilometers below the rim. It sinks 11 kilometers beneath the surrounding plateau. A crater section exposes light-toned layered sediments. These layers appear fractured and faulted by impact forces. Spectral measurements indicate clay-rich compositions. Smectites dominate, while carbonates, sulfates, and chlorite also occur. Such minerals form in water-related conditions. The sediments likely accumulated in ancient lakes or were altered by later fluid flow. Layered terrain rises near an impact crater. The formation shows a striking mesa-like profile. Flat upper surfaces contrast sharply with steep flanks. The layers record repeated depositional events over time. Later impacts cut through these stacked materials. Erosion sharpens edges and exposes internal structure. Each layer marks changing environmental conditions. Differences in resistance shape the geometry. Context camera observations support regional continuity. This landform preserves a vertical record of Martian surface processes. A solitary mound rises from Chryse Planitia. Its slopes expose complex layered stratigraphy. Meter and decameter scale beds stack with clear order. Similar mounds reflect regional scale formation processes. This mound shares those defining characteristics. The layers suggest widespread deposition across the region. Later erosion sculpted the mound into relief. Each exposed band records a separate episode. Documenting this structure links local detail to planet-wide geological history. High southern latitude ground lies cracked and cold. Boulders 1 to 10 meters wide stud the crater floor. They are not random. Stones line up in arcs and straight runs. Some rings mimic polygon ground that forms where ice swells and shrinks each season. Over years, that heave can nudge blocks toward polygon edges. The old polygons may vanish, yet the boulder outlines persist as a durable memory of ice-driven sorting. The pattern matters because it hints at buried ice still shaping the surface. Layered deposits stack across Arabia Terra highlands. Stereo views sharpen vertical relief and expose bed boundaries. With maximum vertical resolution, bed thickness becomes measurable. A digital terrain model can then map each step and slope. Arabia Terra sits in Mars' northern hemisphere. It dates to the Noachian era, about 4 billion years ago. These layers keep a record of early surface conditions, locked into repeating strata and subtle topography. Every band is a time slice of older Mars. A small crater shows debris that seems to push inward. The surface looks smeared along the rim, as if ejecta is moving into the bowl. The behavior is uncertain, and finer resolution is needed to see what drives it. Context camera also captures the broader scene. This terrain sits in Chryse Planitia, the region where Viking 1 and Mars Pathfinder touched down. The site is a natural lab for reading active modification on a dusty plain. More detail will show whether this is impact ejecta or later reworking. Streamlined forms fill the ground like frozen currents. Most of this area is packed with these tapered shapes. Their repeated alignment points to flow that once moved across the surface. This is Granicus Vallis, a complex channel system west of Elysium Mons. The system runs about 750 kilometers long. Both water and lava likely played a part in building these features. The scene preserves a mixed history of erosion and volcanic flooding. That mix makes the channels harder to read and more valuable. Exposed layers sit at the bottom of a trough, not in its walls. The position suggests material pooled on the floor, then became uncovered. The goal is to determine what these layers are and how they got here. Claritas Fossae lies between the lava plains of Dedalia Planum and Solis Planum. It is a graben-filled highland formed before the large Tharsis lava flows. These beds may preserve older deposits that survived later volcanic resurfacing. Their placement helps separate floor fill from wall collapse. A well-preserved crater throws ejecta across a low dust surface. With little cover, small textures and blocks stand out. Context camera hints at many tiny channels nearby, but HiRISE can resolve them clearly. Just beyond the ejecta, round mounds dot the plain. They may relate to hot ejecta melting ground ice, then reshaping the surface as it cools. This target is chosen because the clean ground lets subtle patterns show without being masked by dust. It is ideal for tracking impact-related surface change. An atypical cone rises with flow-like features spreading away. The cone shape implies an older, larger edifice. Its summit area was removed, leaving a crater-like hollow. Inside that hollow, a newer, smaller cone formed later. The surface around it shows flow textures that trace where material moved. This observation aims to resolve the cone profile and the flows in detail. Those measurements can separate collapse scars from younger construction and reveal a multi-stage volcanic story. The geometry holds the timeline. Banded terrain spreads across the northwest of the Hellas Basin. The surface shows repeating bands that cut the plain into textured strips. This formation is only seen in this part of Hellas. The basin itself formed in a giant impact around 4 billion years ago. It is the deepest impact basin on Mars. The banded terrain sits in the deepest part of the basin, at elevations around 7 kilometers. Its restricted location hints that extreme depth controlled the process that built these bands. Few places match this. An ancient river network now stands as ridges. Nearby impact craters hold round mesas inside their rims. This is topographic inversion. Features once low-lying, like channels and crater floors, were filled with lava or sediment that later hardened. If that infill resists erosion, wind or water strips away weaker surroundings. The former valley or crater fill remains high as the landscape drops. These inverted shapes help scientists judge when liquid water existed and where habitable environments were possible on Mars. Thank you for being with us. Please subscribe, share, and like.